Hello, and thank you all for coming for my talk today. Before I get going, I'd like to just say a quick word of thank you, in particular to Thomas Wright for actually getting out of bed and getting the room set up for this talk on campus, and also to John Bayers for actually giving me the idea for, that a talk could actually be done online in the first place. Now, today I'd like to talk to you a little bit about a pretty venerable problem in number theory, that of Goldbach's conjecture. It's been around for over 250 years, getting on for 300 years now. That's when it was first posited, but we think that people have been thinking about the problem for far longer than that. But okay, so what I'm going to do today is talk about the three best and closest solutions we've got to the problem. So I'm going to start by introducing them, as there are three of them there, and then I'll be talking about some of the ways that we've actually got those near-miss results. That's the Hardy-Littlewood method and sieve-theoretic methods. Before I've just sort of got a miscellany section at the end where related results will come into it. But let's start at the beginning. And I'd like to apologize in advance for my horrendous German pronunciation. But so back in 1742, Christian Goldbach, who I'm not aware if he did anything else particularly remarkable mathematically, he wrote a letter to Leonhard Euler, who of course did many remarkable things mathematically, being one of the most prolific mathematicians of all time, despite horrific physical obstacles like blindness and things like that. But he wrote a letter to Euler, and he said, "Auf solche Weise will ich auch eine Conjecture hasardieren, dass jede Zahl, welche aus zwei Numeris primis zusammengesetzt ist, eine Aggregatum soviel Numerorum primärum sei, als man will, die Unitatem mit dazu gerechnet, auf die Congerium omnium unitatem." I say apologies for my German accent there, but I think that's pretty clear to all of us. For those of you who don't happen to understand pre-industrial German fused with Latin, here's a rough English translation. So he said, "I should like to hazard another conjecture of that kind," referring to a Fermat-like conjecture that he'd posed previously in the letter. "Any number composed from two primes is the sum of as many prime numbers, including one, as one wishes, right down to the sum that consists just of ones." But it's a bit weighty, so we put it in the form, every even number greater than or equal to 4 can be written as the sum of two prime numbers. Now this looks like a fairly sensible conjecture. Now you can see that 4 is 2 plus 2, 6 is 3 plus 3, 8 is 5 plus 3, 1,234,570,890 is 373 plus 1,234,573,517, just off the top of my head. So, there are pretty convincing numerics for this, and we've verified this conjecture up to a height of 4 quintillion. So every even number less than or equal to 4 quintillion, that's a 4 with 18 zeros after it, can be written as the sum of two primes. But being mathematicians and not physicists, we're not content with just evidence. We'd like actual proof, and unfortunately we haven't got that. What we do have is, a couple of years ago, Harold Helfgott produced a series of 3 papers, which actually today he published on the archive, 3 of them essentially in one gigantic 300 something page paper, 317 page paper, and he proved that every odd number greater than or equal to 7 can be written as the sum of 3 primes. Now this immediately implies that, well, we can take any odd number that's written as the sum of 3 primes, can add 3 to it, and we get that every even number greater than or equal to 10 can be written as the sum of 4 primes. By checking lower values, we can actually say greater than or equal to 8, because 8 is 2 plus 2 plus 2 plus 2. But it's a bit tricky to get this down to the previous conjecture. This is called the ternary Goldbach conjecture. The conjecture on the previous page, this thing here, is called the binary Goldbach conjecture. And I've seen a few expositions by eminent people in the field and talked to Harold a little bit as well, and people don't think that we can adapt his method to get the binary conjecture, unfortunately. But, you know, we might be able to integrate it with some other methods which would potentially yield results. So it's the first of the near-miss theorems. The second is due to Linux. Note, these aren't coming in chronological order. So this was just after the Second World War. And he proved that we can fix some integer k. Beforehand, we just fix some k. And then every sufficiently large even number, and sufficiently large will pop up again and again, just means that we can ignore the low values and just consider what's going on essentially in the limit. So some integer k such that every sufficiently large even number is the sum of 2 primes and k powers of 2. So again, this is a nice theorem, but Linux didn't actually manage to find a k, and a lot of very bright people have spent many years getting k down, and the current value of k under unconditionally is that we can take k equal to 8. I think we can do a little bit better under the generalized Riemann hypothesis, but that's where we're standing at the moment. Now we can compare these theorems because they're kind of similar. So we say, okay, everything is the sum of 2 primes plus a little bit extra. And how big is that little bit extra? So Helfgott's theorem says that we actually need to take the set of primes as that little bit extra, and that grows like x over log x. But Linux and Pinson-Ruscher showed that we can take 8 sets of the set of powers of 2. Now that's a very small set, so in a lot of ways the Linux result is nicer and closer to the binary Goldbach theorem, but it's not quite as elegant. It doesn't just involve primes, which makes the Helfgott theorem, in my eyes at least, more elegant. And the third of the theorems that I'm going to talk about today is that of Chen, which was back in 1973, and he proved that every sufficiently large even number is the sum of a prime number and a semi-prime, i.e. a number with at most 2 prime factors. Okay, and actually Helfgott's theorem had a sufficiently large thing going on in there as well. He actually showed that every sufficiently large odd number, but he got an explicit value for that sufficiently large, so every odd number bigger than something like 4 times 10 to the 23 or something like that was the sum of 3 primes, and then did some clever computations involving the Riemann zeta function to get the rest of the zeros, the rest of the odd numbers, sorry. Okay, so the first 2 of these problems were attacked using the Hardy-Littlewood methods. That's the Helfgott and Linux stuff was done by the Hardy-Littlewood method. And Chen's theorem involved the sieve theory, although some sieve theory, I think, popped into Helfgott's proof. I don't know about Linux. I don't think so. But I'm going to start on the Hardy-Littlewood method. Going to delve into some of the details, but then ease off again back to sieve theory, get in some details, and then ease off. So if at any point you feel lost, which I really hope you don't, it will, there will be a reprieve. Okay, so we're going to let R of n be the number of ways that we can write n as the sum of 2 prime numbers. So it's the number of representations of n as the sum of 2 primes. And notationally, we're going to let e of x be e to the 2 pi I x, where I is the imaginary unit and e is Euler's number that we've all come to know and love. And what we want to show is that the number of representations of n as the sum of 2 primes is positive whenever n is sufficiently large. Now, we can write R of n in the form of this sum here. And the reason we can do this is that if p plus q equals n, i.e. if n can be written as the sum of two primes, so the sum is taken over all primes p and q, then this thing is just 1. So we're integrating from 0 to 1 of 1, and that gives us 1, which is nice. So for every decomposition of n as p plus q, we add 1 to our sum. But if p plus q does not equal n, then we're simply kind of going round and round a circle, and we're not actually going anywhere. Our integral is 0, so that's why this equals r of n. Now, by changing the order of summation and integration, we get this expression, and we also split up the e term a little bit. And then by splitting up this e of alpha times p plus q into e of alpha p, e of alpha q, we can write as the square of this sum here. Now, this bit here, this e of minus alpha n, is nice and easy to work with. However, this sum in here is a bit trickier to work with, and that's a lot of the focus of the circle method. And the reason it's called the circle method is, as you can see, because of this exponential here. It's essentially a complex circle, a complex unit circle that we're integrating around. So that's where the name comes from. The analytic number theorists are so very imaginative with their names, I know. But the way we treat this integral is that we don't just look at it from 0 to 1 because of how irregular that sum over primes is. We want to split it up a little bit, and we split it up into what are called major and minor arcs. So we're going to let p and q be between 2 and n, with q being strictly bigger than p. And we know that using Dirichlet's approximation theorem, which is a fundamental result in Diophantine approximation, we know that we can write any alpha, any real alpha. It doesn't have to actually be in this interval, but we're going to choose it to be for the sake of exposition. We can write it as some rational number, a over q, plus a small remainder. This isn't anything particularly staggering. It just says that every real number is pretty close to a rational. And we're going to form what are called the major arcs of a and q. So those are going to be the set of all alpha in 0, 1, which are close to a over q. And by close, we mean less than this over here. And the total major arcs are all of these whenever a and q are coprime. So essentially we want this fraction up here to be in its lowest form. And we're taking small denominators. Okay? And the minor arcs are everything but the major arcs. Yeah, again, a nice touch of originality. Oops, sorry. Okay, sorry, I've just seen some questions coming up, but the lag's a bit too bad, so I'm sorry, but I'll have to answer them afterwards. So to take a brief example, I'm going to have a quick picture and then come back to it in a minute. So this is a rough idea of what major arcs look like when we've only really got 2 of them, but this is the image to have in mind. So I'm going to take the example of q equals 4 and p equals 3. Then the major arcs become, so m of 1, 1, is this the set of all real numbers in 0, 1, which are less than 1 over 4 away from 1 or 0. They're essentially the same thing. So we get, this is notation for the ball about 0 of radius a quarter. What you have to think is we're taking the first point to be a point on the circle, and then we're going a quarter in either direction. And similarly, we get m of 1, 2 as being this thing, and the other bits come out very similarly. And putting it all together, the major arcs equal everything except for the points a quarter and 3/4. And you generally wouldn't actually choose p to be this big. So if we have p a little bit smaller, then we actually get some actual intervals left out. And that's precisely the picture that we had here. But why does this work? There's not much point in decomposing something just for the sake of it. I mean, sure, you might be able to get better averages, but you'll give yourself a lot of extra work for potentially not much gain unless there's some reason behind it. So the thing we want to estimate is this sum over primes. Remember from a few slides back, this thing here. That's what we want to estimate. And if alpha p, or if alpha is close to a rational where q is small, then this exponential term here, this e of alpha p, actually starts behaving a lot like e of alpha m for some natural number m. And this is because while the primes are kind of badly behaved on arithmetic progressions for small common differences, they're actually pretty well behaved on average. But if alpha is far away from a rational number with small denominator, then we still get that erratic behavior. So essentially we break it into these parts. We applied the really crude estimates to the minor arcs where alpha minus a over q is big, and we have much more sophisticated estimates for when it's small. And that's the main idea behind it. So there's a lot more technicalities that go into it. And, you know, I don't want to give the idea that once you understand this, you'll be able to prove the ternary Goldbach conjecture or anything like that. You know, there's the paper that was recently done, it was 317 pages long. It's there are a lot of technicalities in this, but, you know, this is the rough idea. Okay, so moving on to sieve theory. So this is a very, very old subject, possibly one of the oldest parts of number theory. So it started in the Greek times. The first sieve that we really used was due to Eratosthenes, but then it took a bit of a break from development. The next person who worked on it was Legendre. But again, that wasn't in any serious way. It only really took off after the First World War. But we'll come to that in a minute. So the sieve of Eratosthenes. It's the most famous sieve. If I gave you a list of the numbers between 2 and 100, 2 and 1,000, 2 and 1,000,000, this is, well, if you didn't tell me to sod off, this is the sieve you'd use in order to get the primes in there. So the idea is that we take the first number in our list, which is 2, and we get rid of all multiples of 2. And because we're actually going to want to do this quantitatively in a minute, we're actually going to get rid of 2 itself. So we're not going to be counting all the primes less than or equal to 100, but we'll be getting something pretty close. So we get rid of all multiples of 2. Now we take the next number in our list, which is 3, and we do exactly the same thing. Get rid of all multiples of 3, which looks like this. Now note, for instance, that 6 has been crossed off twice, and 36 and 70 and things like that. Sorry, 78, can't even read. So take the next one, do the same thing, then 7, do the same thing, and we can actually stop there. Because if we've got some number between 10 and 100, so which is composite, but isn't divisible by primes less than or equal to 10, then its decomposition must be bigger than 11 times 11, which is 121, which is bigger than the set we're considering. So we can stop there. And in fact, no matter what x we go up to, we can always stop at root x. But I do want to note just how many numbers have been crossed off multiple times. So obviously 6 has been crossed off twice, so has 15. 30 has been crossed off 3 times, so has 70. And you can see lots of crossings off. If we had gone up to 210, that would be crossed off 4 times by the time we go through it. actually by this point actually. But what we're left with is a set of primes. We're left with all the primes between 100 and 10. And if we did this generally, we'd be left with all the primes between x and root x. And this is actually a fairly nice procedure, and by looking at getting rid of multiples, we can turn this into a quantitative procedure. So when we got rid of multiples of 2, we got rid of 100 divided by 2, multiples of 2, which is 50. And there are 100 divided by 3, which is 33 and a third. Get rid of the third. There are 33 multiples of 3 between 2 and 100. So we crossed off that many. Similarly with 5, crossed off 100 over 5, and 7, 100 over 7, but take the integer part of that. So we can say that the number of primes between x and square root of x, so this here is the prime counting function. It's just the number of primes less than or equal to x. So our 0th order approximation is simply the total number that we started with, which is x minus 1. That's a pretty bad approximation, if you ask me. Just by counting, we can see that there are 21 primes between 10 and 100, but that's clearly quite some distance away from 99. So what we're going to do is we're going to get rid of all multiples of p, where p is prime and less than or equal to the square root of x. But by doing that, we've actually got rid of, for instance, 6, got rid of that twice. And in fact, any number with 2 prime divisors, we've got rid of twice, which is bad. So we put those back in. So this is our 2nd order approximation. And that's exactly what that does. But then we've put in the numbers with 3 prime divisors too many times, so we'd have to subtract those out. And if we keep going, we end up with this expression at the bottom here. Now, for those of you who don't know, mu of x, mu of n is the Möbius function, which is 0 if n contains a square. Note that in our expressions here, that p1 and p2, for instance, have to be different. And if we went to 3, then p1, p2, and p3 would have to be different. So we're ignoring all denominators here with squares in them. And it's minus 1, mu of n is minus 1, if n contains an odd number of prime factors. So that gives the minus 1 here, for instance, and it'll give the minus 1 in front of the 3 prime factor term and 5 prime factor and 7 prime factor term. And mu of n is plus 1 if n has an even number of prime factors. So it gives us plus 1 here. It actually gives us the invisible plus 1 in front of this x here. So if we put n equals 1 in here, we'd get the integer part of x, which is pretty much this here, but we have to subtract 1. So that's where it's all coming from. But as it turns out, this isn't actually all that good for estimating the number of primes in that interval. Oh yeah, we can quite easily extend this to get all the primes less than x by then taking root x as our new x and looking at the 4th root of x and telescoping down like that. But it's not all that efficient. I mean, mu of n is pretty badly behaved. It's conjectured, pretty strongly conjectured, to satisfy a randomness condition, which I don't know enough to actually go into, but it behaves pretty randomly. So it would be nice to actually get some other information out of this. But in order to do that, we're going to have to generalize the problem slightly. So now we're going to have curly a being a subset of integers, and we're going to have Gothic p being a subset of the primes. Yeah, that's a p and not a beta, don't ask. And we're going to define this sifted set of a with respect to p up to z. I'm never entirely sure how to say that. But that's going to be the number of elements of a which are not divisible by small primes in p. Now, quite often we're going to take p to be the set of all primes, but sometimes we're going to want it for more sophisticated purposes, so that's why we're having it in slightly more generality. And we're also going to define this curly A sub D to be the elements of A which are divisible by D. Okay then. So then we can restate our Eratosthenes-Legendre statement as, so this left-hand side here. So if we have A being the element from 2 to x, then we're going to sift out by primes less than or equal to root x. Actually, this root x here should probably be a root x plus epsilon, but for sake of notation, we'll keep it as is. And our integer part of x over n, as it was previously, ends up looking like this curly A sub D, just the number of elements such that D divides it. So that's getting our multiples of D in there, which is a much more elegant statement, but it doesn't change the fact that it's still not a particularly efficient method for calculating the number of primes between x and root x. So maybe we can use it for other things. What happens if we choose different a's, for instance? So if we have A being equal to the set of all n times n plus 2, where n is less than or equal to x, we get that the sifted set of A up to square root of x equals the number of primes less than or equal to x, such that p plus 2 is a prime, i.e. it gives us all the twin primes less than or equal to x. Well, almost. So when we're sifting up to root x, we have to be aware that we're also going to get rid of all of the primes less than or equal to root x. So we actually have to whack those back in as an error term here. If you've not seen big O notation, don't worry about it too much. It just means that we've got an error of about the size of root x. There might be some constants in front of it or whatever, but we don't really care. We're just remembering the size of it. And if we have A of this form, then we have to be a bit more clever about choosing our z and actually our p a little bit. So this, it might not necessarily be all primes, but our sifting set does then start to approximate the number of representations of n as 2 primes. So essentially p is prime less than or equal to n, and n minus p is also a prime, which is our Goldbach problem. But what are we aiming to do with sifting? So we've set up this nice problem. We've got this notation for expressing it. But now we want to do something with it. We want to get some results. So the way we do this is we choose a function g and an x, and x will itself be a function. But we want x to essentially approximate our set A without a subscript, is the general idea. And then g of d is some factor that we put in front of it, which means that it approximates the behavior of all elements of A which are divisible by d. And we're going to put a restriction that g has to be multiplicative. Again, if you don't know what that means, don't worry about it too much. It's just a niceness condition which allows us to work with it well. But of course, this isn't, or this is highly unlikely for any interesting set A to give us a perfect equality. So we have to introduce a remainder term, which is this thing over here. And for similar reasons as in the Eratosthenes-Legendre, we're going to say that D can't contain squares for this, and it has to be only divisible by primes in P. Can't be divisible by any other primes. But again, don't worry about that too much. It's just included for completeness. And this is, a bit of the horrible bit, but I'll take it apart a little bit. So we want pairs of inequalities that look like this. So we want to bound our sifted set both above and below. And the only differences between the upper bound and the lower bound are these functions f here. So different functions, and we've got a plus here, whereas we've got a minus here. Okay, so an x is here to represent the size of A. V here is a product of our multiplicative function g, and this is the reason we want it to be multiplicative for those who are interested, because we can express it as a nice product, and that's going to be a scaling factor. And we've also introduced this new variable w. So w is going to be less than z, but it's not going to be overly important because we've got this function, and then we've got this error term involving w, which is going to be small. So w is not overly important, but it's quite useful in some contexts. And the key thing here is that, so this plus the sum of rd will hopefully be well behaved. But that's another error term. So that's the error term we had in our approximation to begin with, but summed. And capital F here will tend to 1 from above, so it'll decrease to 1. And little f will tend to 1 from below. So as we're taking things to the limit, we should end up seeing that these two inequalities start pinching together, which is something that we like. I'd just like to move on to, so that's the horrible stuff over. And I'd just like to quickly remind you of Chen's theorem. So this is every sufficiently large even number can be written as the sum of a prime and a number with at most 2 prime factors. And in the same paper with essentially the same method, so remember that we saw the sets which approximated Goldbach conjecture well and twin prime conjecture well, and they didn't look too different from each other. Turns out they're not all that different, because in the same paper, he proved that essentially a version of Polignac's conjecture proved that if n is some positive even integer, then you can find infinitely many primes p, such that p plus n has at most 2 prime factors. Right, so setting n equals 2, that's our twin prime behavior going on there. And again, this isn't too far off twin prime, but it's a very different tack from other attempts at the conjecture. But with Chen's first theorem, there have been some interesting developments made by a guy called Kai. So he's written a couple of papers about this, and his best results actually in an unpublished remark, which I got sent a couple of days ago. And he showed that every sufficiently large even number, n, can be written as the sum of a small prime p and a number with at most 2 prime factors. So small here meaning that p is less than or equal to n to some power which is less than 1. In this case, we've got 0.941 as the power. You previously had 0.95 and 0.945, so it's a pretty slowly decreasing index. But unfortunately, Demsda breaks. And I'm actually working on this problem at the moment with Tom Backhouse. I'm doing some of the computations. So this is hopefully where we might actually see some movement coming pretty shortly. Now, what else can we do with sieve theory? So this here is pretty much the first big theorem of sieve theory. The first sieve that anyone learns, well, the first sieve anyone learns is the Eratosthenes sieve, but the first quote-unquote real sieve that anyone comes across is Brunn's sieve, or Brunn's pure sieve. It's an example of something called a combinatorial sieve, which works in essentially the same way as the Eratosthenes Legendre sieve. But he used it to prove that the sum of the reciprocals of the twin primes converges. So we know that the sum of the reciprocals of the primes, we know that diverges. So if we didn't have this p plus 2 here and this p plus 2 condition here, that would go off to infinity. And it would go off to infinity at a rate of about log x. But the sum of the reciprocals of the twin primes converges, which means that there might be infinitely many. It certainly doesn't prove there are only finitely. But it means that there are significantly fewer than there are normal primes. So, and just for clarification, this sum here is, so this would start 1 over 3 plus 1 over 5, then 1 over 5, then plus 1 over 5 plus 1 over 7, and so on. So we'd actually have repeated primes coming up there. And the most recent result we've gotten is that we think that the sum converges to about 1.90. I'm not going to read out all the rest of those digits. So something else that sieve theory has been able to do, it's actually been a very different type of sieve than that used in all the other stuff I've shown so far, is the recent work of Yitang Zhang, which has been helped along by James Maynard and the Polymath Project, which says that there is some k between 2 and 246, such that there are infinitely many pairs of primes p and q which differ by precisely k. So again, there's a similar result to the Chen stuff earlier, but this was done using something called the Selberg lambda square sieve, which is another example of the ingenuity of mathematical or analytic number theoretic nomenclature, in that it's called the lambda squared sieve because it's got a lambda squared term in it for some lambda parameter which gets involved. But this is also done using a couple of different sieve methods. So on to the final section of random stuff which I felt like I should put in anyway. So there's a theorem of Esterman which looks at how many exceptions there are to Goldbach's conjecture if it was false. So Esterman proved that up to some point n, there are going to be no more than some constant times n over log n to the power a exceptions. So this means this is a function that grows a lot slower than n. So to put it in less technical language, but with much stronger connotation, almost all positive even numbers are the sum of two primes, which is a nice theorem. And we're going to call a Goldbach partition some representation of n as a sum of two primes. And recall that we wrote the total number of it before as R of n. And quite recently, it's quite recently been accepted into a journal, Mutavkiev, or however you pronounce that, proved that the number of partitions of even numbers grows essentially like 2 times n over log n squared, which again is a nice result. In analytic number theory, we love these asymptotic results. They're, aside from the usually unattainable, beautifully simply stated every even number sum of two primes result, we like these asymptotic results second best. And there was another theorem by Stijn. I think he proved it originally in 1931, but my colleague Adrian Dudek completed it last year. And so Esterman proved that every sufficiently large positive integer can be written as the sum of a prime and a square free number. So remember, a square free number is one which isn't divisible by any square. So Esterman proved sufficiently large. Dudek got hold of that sufficiently large, and I think with the help of Dave Platt managed to compute the remaining low integers to get this actually rather pretty result. I quite like this one. And there's a conjecture by Maillet back in 1905. So, once you've got Goldbach's conjecture, this is a pretty obvious conjecture to immediately ask afterwards, but surprisingly, it took 160 years or so. And he asked whether every even number is the difference of two primes. There's no real reason to ask why one over the other. My intuition says that Maillet's conjecture is probably easier, but it's less glamorous, so gets less work done on it. But we don't have as good results for it, possibly because of that. 3 years ago, János Pince proved essentially that there's a positive proportion of even numbers. A positive proportion of even numbers can be written as the difference of 2 primes. So there are, quite a lot of them which can be written as a difference, but we don't have an almost all result, at least not yet, or at least not that I'm aware of yet. Okay, and my final slide. Notice I've actually been going through these rather quickly, but oh well, everyone hates a long seminar, so this last problem is entitled Waring's problem. It's a very old problem. As you can tell, the first big result in it came from 1770. And this is the classical example of the use of the Hardy-Littlewood method. So note that we're asking for a representation of an integer n as a sum of kth powers. So we do exactly the same thing as we did with the Goldbach problem. And we say, okay, we're going to let some function be equal to the number of representations, do our little integral jig and get everything nice, and then construct our major and minor arcs. And it all proceeds very similarly, except that the actual sum we're estimating becomes very different. But so the actual timeline of work on Waring's problem is pretty interesting. So g of k is, as you can see, the smallest integer, such that every positive integer can be written as the sum of that many kth powers. So Lagrange proved back in 1770 his 4-square theorem, showed that every even number can be written as the sum of 4 squares, or at most as the sum of 4 squares, because we'd also allow 0 to be in there. And it's trivial to see that if you go through the integers and count up how many squares you need to express them, you'll pretty soon come upon 7, which cannot be written as the sum of 3 squares. So g of 2 has to be equal to 4. So you quite often get lower bounds from it where we say, okay, this number can't be written as any fewer cubes or 4th powers or 5th powers. So we get these lower bounds easily, but it's getting the upper bounds to match them, which is the tricky part. So that was back in 1770 that we got g of 2 is 4. Then in 1912, Kempner and Weiferich proved that you need 9 cubes to fully express every natural number. And then in 1940, we proved that you need 73 6th powers. In 64, we got 37 5th powers and 86 19 biquadrates or 4th powers, which is interesting. Now, you expect this left-hand side here, so this 4, 9, 19, 37, 73, that all makes sense. You'd expect it to increase. And I don't know about you, but I'd expect it to increase at a fairly decent rate. But you'd also kind of expect that the problem would get harder with increasing k. But it doesn't seem to be the case. Now, I've not properly investigated this. I'm nowhere near an expert on Waring's problem. But it could be that there's some relation between squares and cubes, which allow us to get something for 6th powers. But because 4 isn't square free, we can't do the same thing, and 5's a prime, so we don't get any nice multiplicative properties out of it. So that might contribute for why 6 came a lot earlier than either 5 or 4, but it's curious. Now, we know a lot more than this on Waring's problem. I think we've got a fair amount of the next few digits. But this is a pretty nice example of another way that we can apply the Hardy-Littlewood method. And really, it's applicable to any problem where you want to get representations of an integer as stuff. Maybe powers, maybe primes, maybe, I don't know, anything really. But okay, so it's about time for me to wrap up, I think. I've been talking for a little while, and it's pretty late over here. But I just wanted to share a few thoughts on where I think actually some of these problems could lead, particularly the stuff by Chen. So Chen's theorem here. Now, as I said, I'm looking at working with reducing the index on this prime inequality here. But also I think it could be quite interesting to look at putting some bounds on the semi-prime here. And as far as I can see, no work's been done on it, but that could be an interesting way to go. And if anyone feels like doing any interesting number theory, maybe look into that. But also I've not seen any similar work done with Chen's other theorem. So there might be some low-hanging fruit going on there. Again, if anyone's got any free time for number theory. But I guess, number theory is such a wealth of problems, you're never going to be missing any, really. But thank you for listening. Now I'm going to answer some of the questions that have popped up. So the first one being from Sam Bourne, asking where the Q in the decomposition of Rn went. So I'm guessing that you mean this line here. And the Q went because we can write this sum above here. We can break apart the exponential term here as e of alpha p times e of alpha q with the double sum on the outside. And then by moving the sum around, we get essentially the same sum. So there's a slightly missing step here where instead of having the squared, we've got the sum over all p less than or equal to n of e of alpha p times the sum of all q less than or equal to n of e of alpha q. And slight change of notation, and we get our result. I hope that makes things clearer. But if there are any other questions? Fortunately, this is the time where the lag comes into play. So I guess I'll leave it until gets to another 2 minutes. If there are no questions through, then we'll end it there. This is the awkward part of not actually being in the same time zone and hemisphere, and even forget about room. The minimum number for the Dudek estimand result. That's interesting. I don't know it off the top of my head, but I might. This is the advantage of having access to the internet. I might be able to look it up very quickly. So I can provide a link to the paper in the chat. But so the lower bound that Adrian got was, so he improved on Esterman's, because Esterman had an inexplicit result. So the first step was to get it explicit, and Adrian got it to 10 to the power 10, which meant that they needed numerical verification for everything up to that. So they brute forced everything lower, which is a little bit inelegant, but sometimes has to be done. Just hope that a nicer proof which doesn't involve brute force comes along later on. Okay, so Emily says that you missed the start of the major minor up. Is there anything more specific you can do rather than going through the middle bit of the talk again, or? But I'll provide a link to the paper. Oh, apparently comments can't contain links. Oh, well, that's irritating. Well, I'm sure I can provide it to anyone who's curious. So, yeah, any more questions while waiting for specificity to occur? Okay, well, it seems that there are no further questions. So I'd like to thank you all for listening. And hope I've piqued your interest in number theory a bit more and explained some of the sometimes notation heavy side of analytic number theory. So thank you.